Bam! Mr. Tarou, in this algebra lesson, we are going to define what an absolute maximum and relative maximum is. We're also going to define absolute minimums and relative minimums. And then we're going to look at 5 graphs and learn how to identify and state these points of interest on the graph, on the 5 graphs we're going to take a look at. This concept shows up again in either Algebra 2 or pre-calculus when you're graphing higher order polynomials. It also plays a surprisingly big part in calculus when you're looking at differential calculus. Now, it gets more complicated then. You start having to work with derivatives and limits and things that are beyond our understanding at this time. So we're just going to be identifying these just visually on a graph. Now, these graphs, these 5 examples, I'm just going to give you the graphs and we're going to identify, these points of interest, but these graphs in the real world model real life situations. You might be looking at a sine curve that models the tides of the ocean, and if you can identify the maximum and minimums in a sine curve, it's probably going to be a relative max and min, possibly, or at any rate, you might be identifying the times when the tide is the lowest or the highest. You could be some kind of financial analysis and be looking at some kind of graph that models potential profit that you're going to earn off of a new idea or product that you're developing. There's a lot of real-life applications, but in this example, this lesson, we're going to be just, again, looking at 5 graphs that are given to us, not necessarily applied to some kind of real-life setting. Identifying maximum minimums on a function's graph. Well, an absolute minimum exists if there is an a within the function domain such that the corresponding value of y, written as f of a, because we're using function notation, is less than all other y values f of x in the graph, where x is not equal to a. That sounds very mathy, and it is. And there's a lot of good vocabulary words in here that we do need to know and understand, through our studies in mathematics, so, we know what the teachers are asking us to do for a particular question, or we can follow the directions in the textbook. But just in case you haven't been watching all of my algebra videos in sequence, we have a value of a. Well, within that sentence it says value of a is within the domain of your function. Well, right, the domain is your input values, and if you're just talking about a graph on an xy axis, they are the x values. So a within the domain, that's part of the sentence that's telling you that this is an x value, that there is an x within the domain, such that the corresponding y value will f of a, that's where, f is the name of the function, this is function notation, and the variable that's inside the parentheses is the independent variable, the x. You plug in the x, the input value, get out the y. We can name the horizontal and vertical axis with other variables if we're talking about some kind of application setting, word problem setting, but Cartesian plane, it's x and y axis. So x and y is less than, so this value of f of a is giving some kind of y value, and that y value is less than all the other y values, and this f of x means, just any value of x within the domain, that you're getting some value of y, that this y is less than this y over the entire graph, except for when x is not equal to a, everywhere that x is not equal to a, because, well, to put it into a picture so you kind of understand what I'm talking about here, we have a parabola that's opening up. Now, because this parabola opens up, there's one point that's at the very bottom of that dip. Well, at the bottom of that dip, that's going to give us our smallest y value. Remember, the y values are the up and down movement. There's some point at the bottom that gives us the smallest y value that's included throughout this entire domain of this graph, because from this point, the vertex, the graph opens up in both directions. So that y value is the lowest, the smallest y value within this entire domain. So that point, that vertex, when you, if you haven't studied thoroughly your parabolas yet, this is just for purposes of pointing out what a absolute minimum is. But for that value of a, that x value of a, f of a, the y value of that point is less than the y value that you're going to get from plugging in any other value of x within the domain, right? And of course, domain is, again, that horizontal movement along the x-axis, or any x value that you can plug into the function and get some kind of real output. And if a was equal to x, since a is an x coordinate, if a and x were representing the same numerical value, and they can't because they're different letters, you'd be looking at the same point, right? And we're looking for that absolute lowest y value that's included within the graph. So I hope that makes sense. A relative minimum exists on an open interval if there is an a in that interval such that, again, f of a, and we see the a again in the parentheses, so it's still an x value, that the y value that we get, the whole f of a expression, that y value that we get by plugging that particular value of x into the function, is less than the values of y we get from plugging any other x within that function that's in this open interval. Okay, well, maybe you have either not learned or have forgotten what an open and closed interval is. So let me get this out of the way. Remember graphing inequalities on a number line? An open interval is some kind of example where we have, in this case I have written that c is less than x, or x is greater than c. And then that x is also less than d. So to put some numbers to it, here's an open interval. Here's an x which is greater than 1 and less than 4. So any value of x that's just a little bit bigger than 1, like 1.000000001, would be good. And any value that we can put in for x that is less than 4, even if it's 3. That's a little bit, any value, any numerical value between 1 and 4 is a solution, if you will, to this open sentence. So to graph it on a number line, you'd put an open dot on 1, an open dot on 4, and shade between those open dots. Now that means that the value of 1 is not included in this interval, and nor is the value of 4. It's an open interval. A closed interval is when you include the endpoint. See the equal signs here now? And when I graph it on the number line, those dots are closed. So when we're talking about exists on an open interval, well, let me get the phone. Alrighty then, and I'll be pointing out the importance of paying attention to this idea of open and closed interval as we go through the examples that are in this lesson. And it might seem like a little bit of a technicality in this definition, but it does have its point where you do need to pay attention to it. Now, getting this drawing back up here, my picture-in-picture, very high-tech. We've already discussed how this parabola that was opening up had an absolute minimum. There's just one point on this graph that has the lowest possible y value, and so there is an absolute minimum here. And now we have kind of what's looking like a cubic function, and it goes up forever and it goes down forever. So the fact that it goes up forever means that that graph has no absolute maximum. It just keeps going up and up and up. And as soon as you say some y value that you think is the greatest, well, it's just going to go up a little bit higher. And it also goes down forever. So that graph does not have an absolute minimum, and I haven't defined it, but it doesn't have an absolute maximum yet either. I'll go a little bit faster on the second half of these board notes. But it does kind of, as you read it left to right, it kind of does dip down, and there's a bottom there. It kind of looks like the one that's over here, and then it rises back up again. So it does fall and then start to rise again. And this cubic function, I know in Algebra 1 maybe you haven't been exposed to cubic functions yet, but it does have a domain of all real numbers. There's no breaks in this graph. I can draw the entire graph without ever picking up my pencil. A little bit of a preview of definition of continuity there. But okay, so there's some kind of open interval from b to a. And remember, these are x values. So there's an x value here and there's an x value here, and a is somewhere within that open interval. And now, for this notation, we also need to assume that x is within that open interval as well. So within this interval from b to c, this open interval from b to c, a is greater than b and less than c, there is that bottom point. We can see it. So mathematically, all mathy talk, that means that f of a, within this open interval, there is an f of a. There's a y value that you get from plugging a, that x value, into the function. You get some kind of y value that's going to be less than, smaller than all the y values that you get when you plug, well, all the other y values that you get when you plug x's in between b and c. All those other y values, when you plug in any other value of x on this open interval, that y is going to be smaller than that y, again, assuming a is not equal to x, because then you're talking about the same point. So absolute minimum and relative minimum. Graphically, we're going to do a bunch of examples, but this is such mathy language, I thought that would help you to hopefully understand these definitions. Now this half is going to be much quicker because it's just the opposite. An absolute maximum exists if there is a b within a function's domain, within all the possible x values, such that the corresponding f of b, get a y value that you get when you plug in b, is greater than, right? We're talking about a maximum value and then the graph starts to fall again. Greater than all the other y values, f of x. And if you really understand function notation, I'm being a little bit redundant in how I'm writing this sentence because you should know, if you understand function notation, that that is a y's. But I'm telling you twice basically in the same sentence that, hey, that means y. In the domain where, again, x is not equal to a, because then that would be the same point. A relative maximum, not an absolute maximum, exists on an open interval if there is a b in that interval such that f of b, see the b again inside the parentheses, so it's an x value, that f of b is less than f of x, that this y is less than that y, any other y that you can possibly get from any other x on that open interval, assuming that x is not equal to a. Okay, so that is all the formal mathy language of definitions for absolute max and min and relative max and min, except I'm now saying that in reverse from how I'm pointing to it. So let's get one at a time. We're going to take a look at 5 graphs and identify the absolute and relative max and mins of those graphs if we can. So here we have our 5 graphs. We're going to identify any maximum or minimums, whether they're relative or absolute, for each of these graphs. We have sort of a weird thing here. We got a graph that's rising to the left and rising to the right with a few dips in the middle. We may learn later in our algebra studies that that looks like a polynomial to the 4th degree, graphing higher order polynomials. And we're going to find a relative max, if there is one. Is there an open interval? Is there a place within that graph that you see where it kind of, as you read it left to right, that it kind of rises and then falls? Well, it's falling here and it dips down. That looks like it's going to be some kind of minimum because it starts to rise up again. Remember, when we're looking for relative max, or, well, forget the word relative. When we're looking for max and mins, we're looking for y values. What's a high or low y value? And the y values are increasing because the graph is rising to the right, and then we get to this blue dot and it starts to fall again. So it seems like somewhere here, maybe an open interval from where x is greater than, oh, I don't know, 4 to 6. Within that interval from 4 to 6, if I look at there, the graph is rising and then it starts to fall again. So it looks like that we do have a relative maximum there. Now we have a relative max of 1, 2, 3, 4 at 1, 2, 3, 4, 5. So we have a relative max of 4 at 5. Now it is, identifying the max and mins is about the y value, but I like to also identify where that y value is at. So we do have a relative max again of 4 at the x value of 5, and the maximum is the 4. Now, is there an absolute maximum? Well, we do reach a high point here and the graph starts to fall, but then it starts to rise up again. And on both sides, to the left and to the right, as x decreases and as x increases, that graph starts to shoot up, and those arrows mean that it never stops going up. So there's never going to be a sort of real y value, which is the greatest, because as soon as you say it's like a million, well then I can just keep going up and say, no, it's 1,000,001, 1,000,002, 1,000,003, or a trillion, or a billion, a zillion, whatever. There is no absolute maximum value. Is there a relative min? Again, is there some kind of open interval where the graph has a minimum value, whereas you read it left to right, the graph is dropping, and then it starts to rise again? And it can be a sharp bend or it can be a smooth curve. Well, it's falling to the right and then starts to rise again, so it seems like at that x value of 2 we have a small, or the smallest y value that exists, and it starts to rise up again, and then it starts to fall again. So there's actually 2 minimums. There's a minimum y value of 1, and there's a minimum y value of, looks like I try to make it about a y value of 3. Well, 1 is less than 3. So The 1 is going to be an absolute min for that entire, and the absolute mins are about looking at the entire domain of the graph, with including all of the x values from negative infinity up to positive infinity. What's the smallest y value that is included in that graph or throughout the entire domain? And that's going to be 1. So we have an absolute min of 1 at x equals 2. And then I can see this point here on this open interval, say this open interval from where x is greater than 1, 2, 3, 4, 5. I should have put some numbers on here. And really, well, I could say really any x value, but let's say x is less than 6. On that open interval from 5, or that would be 7, wouldn't it? From that open interval of 5 to 7, the graph falls and starts to rise again, and we can just visually see there's a bottom there. So that's a net relative min of 3 at x equals 6. Okay, and again, your book might just be using the 4, the 3, and the 1 for identifying the extreme values, so the maximums or minimums, whether they're relative or absolute. For this graph here, we have another graph that has end behavior which is the same. It's going down to the left and down to the right. It's a parabola. It looks like a parabola anyway. It's opening down, and throughout the entire domain, there's no breaks in the graph. It kind of is a continuous curve going to the left and right forever. Well, I can clearly see that there's a top to that parabola. Later, if you haven't studied parabolas, we'll know this as being the vertex. And the y value of that vertex appears to be 3. So we have an absolute max, where's my yellow chalk, of 3 at, and I'm just writing the x to be redundant if you really understand the language of identifying absolute max and mins, but maybe we don't because we're just learning it. So we have an absolute maximum y value of 3 at the x value of negative 2. Now, a relative max, well, there's only one maximum in the graph, so really there's some kind of open interval where that y value of 3 is going to be the largest y value, but it also is the same as the absolute max. So the relative max and the absolute max are kind of the same thing, but the absolute max is more of a special case because it covers the entire domain. So I'm just going to identify that as our key point of interest. Now the graph goes down forever. There's nowhere as you read that left to right that it kind of falls and rises back up again. So there is no, because it goes down forever, there are no relative mins or absolute mins for that matter. Now over here, we're going to play with this third example a little bit. It's a great example, and I also find it a tad bit frustrating. We can see, let's see here, is there a relative maximum value? That's the one that I kind of struggle with the way that relative maximum is identified, or not identified but defined. I checked 3 textbooks just to make sure I was going to say it right in this lesson. A relative max was about that a within an open interval such that f of a was greater than f of x on an open interval. I can see that there's sort of like a top value here. This is at the point negative 2, left 2, and up 1. So this is the point negative 2, 1. And then we have a point over here of 3, 4. Well, if I just look at like this portion of the graph, then that seems to be some kind of maximum. But I can't identify the 1 at negative 2 as a type of maximum, which really seems weird because over this entire graph, and no, there's not arrows extending on. This is it. It starts here, falls, and goes up and stops. There's no arrows. There is a maximum of 4 at 3, and within this entire graph, that 4 is an absolute max. That value of 4 is greater than every other y value within this function's domain. And by the way, the domain of this function is from negative 2 to positive 3, including those values. And the range, I have another lesson about identifying domain and range from a graph. which I'll put a link here if you need help with that. The range goes from -2 up to +4. And within that domain of -2 to +3, 4 is the biggest y value. So we have an absolute max of 4 at x equals 3. And again, that 4 is the maximum value that we're concerned with. I'm just adding a little extra information about where it's at. And I really want to say that we have a relative max of 1 at -2, but I've checked 3 textbooks and none of them would identify that point as any kind of anything special. It's just an endpoint. Because when you're identifying a relative max, all the definitions say that when you're identifying a relative max, it needs to be on an open interval, that there is an a on an open interval such that f of a is less than f of x. Well, if I make those dots hollow, indicating an open interval from -2 to 0, then there's no place where the graph goes from falling to rising, or, well, we're talking about maximums. There's no place where the graph rises and then falls again. That -2, 1 is just an endpoint. So no relative max would be identified because that is at the endpoint. That would be at the endpoint of a closed interval. And identifying relative max and mins are always about identifying, a lowest y value, if you will, on an open interval. So sorry, I just find that a little bit bothersome, but that's the way it is. So relative min, well, there's only one point. Oh, I hear the static. Let me try changing the channel on our radio here. Okay, let's see if that helps. So we only have that one minimum value. So the relative min and the absolute min are they're going to be the same point, if you will. And again, that absolute min is, well, I'm just going to identify it there. We have an absolute min of -2 at, and this time I'll write the x, at x equals 0. And the relative min, absolute min, kind of the same thing, or at least are the same point. The lowest y value in that entire domain is -2 at x is equal to 0. Okay. Now, let me change this problem up a little bit. If I were to make this dot open, then there's still an absolute minimum of -2 at 0, and this has sort of like it goes to a maximum of 1, but then there are places in the domain where the graph goes higher than 1. But if that's an open dot, where are we stopping at? Now, we're approaching the point 3, 4, but we're not getting to 3, 4. We're getting to, like, oh, I don't know, how about 2.8, 3.7, or 2.9, 3.9, or 2.999, 3.999, or 2.99999, 3.99999. I can get infinitely close to that open dot, and I'm almost getting close to wanting to start talking about calculus, but we're only in Algebra 1. But we can get infinitely close. We can approach that open zero, that open dot, excuse me, but never actually get to it. So I can't say that there's a relative max or an absolute max now, because I can't identify that as a relative max because it's not going to be, it's on an endpoint. It's not part of an open interval. Seems really weird to say. And there's not an absolute max because we're getting really, really close to that open dot, but I'm not including, like if I were to talk about the domain of this graph right now, the domain is all x's from -2 up to, but not including, 3. So if 3 is not part of the domain, then I never get to the point of 3, 4. So there are no maximums, relative max or absolute max, in this graph. Again, can't call that a relative max because it's not on an open interval. We're not identifying it on an open interval. There's just an absolute min of -2 at x equals 0. Now, if I come up here and I just mess with this a little bit more, and I make that an open dot, and then maybe I put a dot right there, so now the domain is, let's go ahead and close, well, yeah, let's go ahead and, let's leave that open. Now, if I just, again, put an open dot where there was one at the sharp bend and put it up here, just kind of, and then pop it up there, my domain is still going to be from -2 to 3 with an equal sign and an open inequality. The range, what y values are included in this graph? At least the way it's drawn right now. Do we have a y value of -2, or does it just approach a y value of -2? It's an open dot. So our y values are going to be greater than -2 and less than, again, not actually reaching, excuse me, that point of 3, 4, but we're approaching that open dot of 3, 4, which means that that x value of 3 and that y value of 4 really can't be included in the domain. Now, is there an absolute min? Is there a graph at y equals 0? Yeah, right there and there. Is there a graph at y equals -1? Yeah, right there and there. Is there a graph at y equals -2? Not if there's an open dot. It's there at -2. Is there a graph at -1.999? -1.99999? Yes, but not at -2. And the way this graph is drawn, there's not an absolute min or relative min. There's not an absolute max or an absolute max. And so they can get a little bit tricky, these problems, just looking at a picture of identifying relative and absolute min and maxes. Oh, let's see here. How about just one more variation? If I come through here and let's just put in, doesn't really matter, an open or closed dot there, now that point would work for, at least the way it's drawn now, an absolute max of 1 at -2. Okay, I don't know how many examples that was I just did, but it was all off of that picture. Now, these last two problems, these last two graphs of 4 and 5, I've kind of scrunched them down into the corner. Why is that? Well, it wasn't quite because I was running out of room, but it's also because this graph goes down as we go to the left. That graph is going down forever. Now, it seems to be flattening out, but do you know something called an asymptote? If you're just, we're very early into our study of algebra, at least that's how I'm making this lesson, and I don't think my book has identified what an asymptote is yet. So that can be kind of a problem. I have to clear that up with my students. I'm not sure if you've heard about asymptotes yet either. I'll put a link here about learning about horizontal asymptotes if you like. As this graph goes to the left, it's getting closer and closer and closer and closer and closer to y equals 0, but it'll never approach it. And it's going up forever as you go to the right. So the domain of this graph, I really didn't intend on making a lesson about domain and range. I've already done that, but understanding how to set up domain and range will explain why this graph, it has no maximum or minimums. And a fancy name for it, as you read it left to right, it's always going up. It's monotonic increasing. That's something I've defined for my students already. The domain of this graph, it goes left and right forever. So the domain is, x is greater than or equal to -infinity, not -8. And whoops, I can't write it that way because it's sort of a theoretical number. X is greater than -infinity and less than +infinity. You might see that as -infinity to +infinity if your book is using interval notation. Your teacher might also just say that this domain is all real numbers. Just to put it in sort of like English, not number 15. Well, it still looks like a 15. There we go. Now the range, the output values, the y values, if you will, the range is what we're dealing with when we're identifying max and mins. The y values. What's the lowest y? What's the greatest y? Is it happening on an open interval? Is it the lowest y in the entire domain? Well, the range of this graph, again, approaching 0, and then going up forever. There's no concrete. It's approaching 0. It's never going to become 0. It's just going to be approaching it. So it never becomes a concrete, real minimum y value. And this goes up and down forever as well. So neither one of these graphs has a relative or absolute min or max. Okay, that is the end of my last example. I hope you now understand how to look at a graph and identify at least these particular points of max and mins. I'm Mr. Tarrou. Go do your homework. Oh, by the way, in the description of this lesson, if you've watched this long, thank you very much, I will include a link to identifying max and mins using calculus, just so that you know that this stuff is going to come around again in your math studies if you do, get that far in math.